speakers are Mr. Manoharan Rajbhushan, Vice President Reliance GIO. He has worked throughout in various capacities in the field of plant automation. For the last 15 years, he is working with Reliance Industries Limited. Next, we have with us Mr. Takaya Watanabe. He is currently working as the General Manager, Business Development and ICT Solution Department, Energy and Environment at Mitsubishi Heavy Industries, Tokyo in Japan. He is a well-known expert in thermal power plant, nuclear power plant, renewable power, clean coal technology and coal gasification battery. Next we have along Dr. B. St. Chaudhary, Executive Vice President and Chief, R&D, Industrial Excite Industries Limited, working in field of lead-acid technology for more than 30 years now. And lastly, we have along Mr. Archan Padmanabhan, an engineer and entrepreneur with expertise in research, development and commercialization of energy technologies. Currently, he leads product strategy and application engineering for the energy storage group at Tesla. A big round of applause for all the speakers for this session.
Thank you. Thank you all for staying back. I can assure you that this session is going to be worth your time. We have an amazing panel here. As we have seen over the last 2 days, energy storage is becoming more and more relevant, and maybe one sector where in India particularly we don't need any government intervention is commercial and industrial application. Of course, always better regulation, better framework will always help to make things better. But as we have seen here, and we'll have the first presentation from Reliance Jio, Mr. Manoharan Rajbhushan, who is going to talk about how Reliance Jio went about looking at energy storage systems and took the decision for investing almost close to $300 million on looking at lithium-ion batteries, which is actually maybe not very well known in the industry because Reliance has kept their lips pretty close. But probably I think it is the largest purchase of lithium-ion batteries in last 1 year, probably except for Tesla. So, but anyway, without any further ado, I'd like to hand it over to Mr. Manoharan.
Hello. I thank Energy Storage India for having given me a chance to talk to such an informed audience on the subject of energy storage. I'm going to today talk about Reliance Jio initiative of using energy storage in the telecom application. In particular, it's going to be more about telecom tower application, where it has got more wider acceptance, wider application in the telecom tower, more relevance in that. As of today, the system that exists in most of the telecom towers, we have about 350,000 towers all over India by various telecom operators. And this is how it works, like as telecom service is providing 24/7 without interruption the service. There's always a battery backup since the power is not always available, so there's always a battery backup. As batteries are expensive for very long outages, like whole day if there is no power, you can't run on batteries, so there is a diesel generator invariably in all these towers. When power from electric grid fails, it gives a signal to start. When there is a power available in the grid, there is a healthy phase selector which selects the healthy phase and gives to the SMPS converter, which converts and gives 48 volt DC on which the telecom system operates. So whenever there is a power failure, the diesel generator is started. The controller is giving a command, gives a command to the generator to start, and then it starts supplying the energy to the telecom tower. In the duration of changeover, battery comes in as a bridge. It comes more as a right-through power. And during there are many strategies that each one follows now. In order to reduce the diesel run hours, they don't start the DG immediately on the power failure. They rather discharge the battery to a certain extent for a few hours or to a certain state of charge and then run the DG. Or sometimes during silent hours where neighbors complain, then they don't run the DG from 12 o'clock to morning 5 o'clock. The DG is never run, the battery is put on load. So they based on the strategy what one follows. This is how the system looks like, a typical system looks like. Based on the strategy that follows, it determines the size of the battery storage system. So this is how it looks like. There's a diesel generator, there's a battery backup, then there's AC power from the utility, and then there are rectifiers, and then there are the rest of the distribution systems. And now very soon we'll talk about it. This diesel generator is getting replaced in all these places. As many as more than 200,000 sites, there are diesel generators available now, which are slowly getting replaced for the reason that we'll discuss now. So the key challenge is grid power is not available on 24/7 basis, as you all know. Power quality is very poor. It gets so low voltage sometimes you can't use that power at all. Then increased fuel costs every year, and then high maintenance costs. Use of DG creates pollution, as we know. Fuel theft is very rampant since the whole service is contracted to the outsourced to the contractors. There's a lot of system of theft, rampant theft taking place. And then there's also a directive from TRA saying that we need to shift to green energy. That is about, there was a directive which has not yet come as a government rule. It's not come as a rule yet, but the 25% of the urban sites have to be on got to shift to green energy, and 75% of the rural sites have to go on green energy. This was what was circulated, but it's still not come as an order, but any day it may come, and then we need to, this is a challenge the telecom sector will have to face because it involves a lot of capital expenditure to subscribe to this kind of requirement. The preferred energy storage device for telecom should be low TCO, total cost of ownership, high energy density because of very small space available, high reliability should be because they're all unmanned sites, okay, and high service life under cyclic load conditions. Since power is not very steady, it keeps on site. The battery comes on load very often, so it's a cyclic load. It's not a very fixed load to that extent. So it should have high life on cyclic load. Maintenance free. The current batteries which are there are quite maintenance prone. It requires cell utilization to be done every 18 months. Otherwise, you lose it. You don't even get 2 years of life of a battery. So what we're looking for is essentially a battery which is maintenance free, environmentally benign. The lead acid battery is not so very environment friendly, as you know. Then should be less prone to theft. The lead in the lead acid battery is an attraction for thieves. They steal the battery. So the new technology should avoid that as well. And then less sensitive to ambient temperature. Now we'll come to that again. It should not require air conditioning for at least 50 degrees. Available energy storage device today, what is available is batteries, flywheel, compressors, energy storage, and superconducting magnetic energy storage, supercapacitors. They're all there, but none of them are as proven and as readily available. I mean, not well proven, they're still not very mature. So battery, the technology which is more mature, which can be rolled out as of today. And a quick comparison of the batteries that are available. These are all well proven batteries in use for over 2 decades. Lead acid, nitride battery, lithium, nickel metal hydride, then lithium ion, sodium. If you see all that, you'll find only lithium ion has got a very good cycle life as well as very high energy density. So it becomes an obvious choice, though the cost is high as of now. The capital cost of lithium ion battery compared to the conventional lead acid batteries is quite high, but even then over a period of time with all these advantages, it's able to, the total cost of ownership is still within the striking range now to make the shift. And the shift is already happening. Reliance is taking the lead to deploy 100% lithium-ion batteries only in the telecom, and other telecom operators are also trying to follow suit. They're waiting for our experience in the team. We're not yet rolled out. Rollout will take place sometime in the first quarter next year, and so everybody's watching the performance of the lithium-ion battery in the telecom sector now. And this is a quick comparison of lead acid with the lithium ion. So you find that you see the insulation space is higher in lead acid, and similarly system weight is high. Then the temperature range, if you see, the lithium ion can go up to 50-55 degrees, and then charging rate is very fast. So when you have very erratic power, even if you have 3 hours power, you can charge the battery. Lithium ion battery can be fully charged, 100% charge can be done in 3 hours time. And it's a quick charge this thing. And then cycle life is 2 to 3 years for a lead acid, which is also quite difficult to get even that 3 years. Whereas this one can go to 8 to 10 years depending on how we make use of it. I mean, there are a lot of other things which needs to be done when you deploy a lithium ion battery. We'll come to that in the next few slides. And achieving 24/7 operation. New technology in telecom, particularly the 4G technology, as well as even the 3G, the electronic footprint has come down now compared to what it was 10 years ago. The electronic footprint hardly requires 1.2 kilos or 1.2 kilowatt. Not even that. Many of them in the 1.8. There are some in the 700, 800 watts range. And then the electronic by itself, the equipment is able to tolerate 60 degrees, which was not so earlier. Earlier it used to go on a thermal shut-off around 45 degrees. Today the electronics does not require air conditioning. So the batteries were the only thing which were requiring air conditioning. Here it requires 25 degrees to 30 degrees to be maintained if you have to get even that 2 to 3 years life. So people built a small cooler for the battery. So in the market it came a battery cooler with 300 watts energy being used continuously just to cool the battery. So now it's possible with the lithium-ion battery to completely eliminate the air conditioner. And then with that, it's possible now we have seen if you get 6 hours of power in a place, even if it is not continuous, you get 3 hours and then 3 hours later in the day, you can run the site without any DG. So this is a very paradigm shift that is taking place. And all the operators are shifting to that. And the cost of the lithium-ion battery also is coming down. In the last 18 months, it has come down considerably. And another 1 year or so, it's still likely to come down, not very much, but it is following a downtrend. And at the moment, it's as of October, the price is around $326 per kilowatt hour, is what is the street price. And it's still likely to come down marginally. So that makes it very attractive to migrate from traditional VLL battery to lithium-ion battery with all its advantage. This is more of an electrochemical part of the battery. I'm going to skip this. Then, yes, the advantage of lithium-ion, high energy density, low volume, low weight, low TCO, total cost of ownership is coming in the striking range because of the reduction in the price, the recent price, and can be used in partial state of charge application, which is very normal in telecom. So since you don't get power regularly, battery never gets charged to 100%. It always remains in 80-85% in the best. Whereas and then it gets damaged. I mean, the sulfation starts, the electrodes start sulfating if it remains for several days on a partially state of charge. Lithium has got no such problem. You can run the battery completely throughout its life with a partial state of charge. If you want, you can charge it to 100%. If it doesn't, if you are not able to charge it to 100%, the battery doesn't get affected. That's a very key advantage in a telecom application. Can be used in deep discharge application as well, suitable for high temperature. So we don't need air conditioning. We're not going to install any air conditioner anymore in these telecom towers. So this has got that, lithium battery has got that advantage. Then another advantage is low temperature. Even in low temperature, this gives very good performance. Sub-zero also zero, whereas VLL does not give very good performance in the sub-zero level or zero level also. High discharge, then low self-discharge, and very high round-trip charge energy efficiency. VLL is around 85%, and lithium-ion is around 96%. So when you have 2 cycles a day or minimum 1 cycle a day, all this matters. That also costs energy because of the cyclic charge and discharge efficiency. There are some disadvantages. I wouldn't call it, I think I should have called it disadvantage. There are some caution to be in the cell. The lithium-ion is very sensitive. It can have thermal runaways and can have problems of its own if it's not taken care well. So cell level protections are required. So every lithium-ion battery that is sold is never sold without its own BMS. There is a battery management system built into every battery that is sold, other than the batteries that are there in our mobile phones, all other batteries which are about 10 ampere hour and above, invariably they come with a lot of electronics inside to protect the cell. Then poor tolerance to overcharge. Overcharge can lead to meltdown. That's a big problem with the lithium-ion battery. Lithium dendrite formation due to cyclic charge discharge and exothermic reaction, if it ever happens, between charge electrode with electrolyte solvent and separated material can lead to thermal runaway and can eventually melt down completely. Technology maturity is also a problem as of now. The technology is evolving more in terms of making it adaptable to all applications, like there's a BMS, and then if you have in telecom, you'll not use just one battery module, you'll use a couple of modules in parallel. So when you use all that, then there must be a system which should take care of managing the bank of batteries with several modules. So invariably it has got another additional control. The one you see on the left on the yellow color is what is there inside the battery. Okay. And the one on the blue color, that is the one which is taking care of multiple batteries when they are connected. This is a central BMS, it is called. The one within the battery is a BMS, battery management system. The one outside, the bluish one, is a central BMS, which when you have several batteries connected in parallel, it has to ensure they all charge up to the same level, and it has to monitor the performance of all of them. So there is a central BMS. Actually, the central BMS, what is shown as blue here, is invariably this many. If you have 6 batteries connected, you should have so much electronics inside to take care of each battery module. So it's quite sophisticated, this lithium-ion battery. But it's still evolving. When I said about maturity, what I meant in this slide, technology maturity. Now they have done away with the central BMS. They're trying to put all the functions in the BMS itself within the battery. And then when you set up multiple batteries, then you set up one of the battery by a toggle switch to act as a master. Then it assumes as a master and does the same control what the central BMS does. So there are a lot of new technologies which are coming up. Some batteries don't have the central BMS. They have the same thing what I said. One of them assumes as a master and runs as it works as a BMS as well as a CBMS, central BMS. So these are all changing, and then they have challenges like this. Module isolation due to overcurrent, and there are several modules in parallel. One of them isolated, you're losing the capacity of the battery bank. So module will get isolated because it has got a BMS inside. In case something goes wrong inside, it becomes warm or something, its cells go warm, then it trips. So to control all this, it requires a lot of integration. Battery module protocol demands to decrease maximum charging current limit with respect to the area. It's not one charging current limit for a particular battery. If you have a 75H battery, it is not that charging current is limited to 15 amps or 10 amps. Depending on the age of the battery, the temperature at which it is subjected to at that time. Lithium-ion battery gives you, the controller gives you a value for the controller, the charge controller to take care of it. Accordingly, adjust dynamically the current limit. You know, see this diagram. There's a yellow, the last corner, there's a yellow thing, and then there's a wire connected. So the controller talks to the central BMS. So all this communication keeps on going between these two to optimize that. So based on the new current limit that is sent by the controller should adjust itself to reset the current limit of the entire battery module. These are all very sophisticated controls that needs to be operated. If you really want to get that full 3000 cycle and 3500 cycles of lithium-ion batteries life cycle, all this needs to be done. You can't just install the battery and just leave it. Then you won't get. That is a sophistication that needs to be built in when we migrate to lithium-ion battery. We have done all that in Reliance. We have seen to that. We have integrated this. We will come to that. So this is what it says. See, suppose you have 3 battery modules each with 0.3 C current limit. If you don't have all this loop controller or what I said, you see when 2 of them trip due to protection, the battery goes into protection mode. You will find all the current will flow into the third one. And it will trip that as well. See, 0.9 amps is 0.9 C is going to the last one, which is still on circuit, which is still on right. So you will trip that as well, and you lose the entire bank, you lose the cycle. But if you have a closed loop, you will find that it knows how many modules are right,
how many of trip, and what is the recommended charging current. And accordingly, you see the last one, which is F2 trip, which is still on there, its current is still 0.3 only. The controller takes care of all that. Controller, that means there should be constant communication between the BMS and the controller. So this is what it is. So all these applications are needed.
And then the other maturity part, when I say technology, is the challenge is, it's also a challenge, and the maturity has not still happened in the industry. Communication protocol between each of the manufacturers is different. So when you want to integrate it with the controller, it has got a Modbus, it has got some batteries have got a CAN bus, some batteries are ASCII protocol. To integrate all that with your controller, it's a challenge. Because if you want to change it tomorrow, the battery, then you have to have a setting in that. The controller should say that now this type of battery has been replaced with the other battery, then it should change the protocol and now start communicating with the new protocol. These are all the challenges. And yeah. So SMS controller integration with BMS, battery charging, all that. At any point you can connect here. So skip this. And this is how a typical integration with the BMS, with the battery, with the SMPS controller, with the small gateway and all of the GMM gateway, battery module gateway. All this was needed to make it work. This thing, and then we also have to take some of the parameters all the way to your network operation center for remote monitoring. These are the typical signals which we take it all the way to the thing. For all the 80,000 hours we have done this, all these modules are, the parameters are being taken to for a central monitoring. Similarly, the alarms, the earlier one was one parameter. These are so many alarms. You'll see about 19 alarms for each bank. If I have about 6 battery banks, 6 into 19, that many alarms have to be carried to the central monitoring to ensure. Because if you don't have this integration, you will be totally blind. And then you will find when the battery fails and there's a data logger in the battery, you will find it has given us typical alarm like cell temperature out of range several times for the last 2 months, and we have not cared about that, and then it will fail. So it's better to have a proactive action. Therefore, you need alarm monitoring in the network operation center. So these are the challenges. This needs to be integrated, and we have done all this integration in the Reliance Jio project. And the summary is lithium battery is ideal choice as of now for telecom tower energy storage device. Possible to operate telecom tower on a 24/7 basis without the need for DG in almost nearly all the cases. 90% of the installation can manage with battery. Then it requires robust integration with BMS and the power system as I described now. And it requires proven protection features in the BMS to avoid any vulnerability. Thank you very much for listening to the
So without any further delay, I would like to invite Mr. Takaya Watanabe. He's going to talk about not just the innovation and about technologies, but about some of the new business models which Mitsubishi is trying to introduce.
Thank you, Rahul. My name is Watanabe, and I'm from Mitsubishi Heavy Industries, Tokyo, Japan. Our company is Semedo Technologies. We have about 23 companies and factories and offices in India, mainly dealing with the technology like power related, the gas turbines, steam turbine, boilers, and all energy storage, as well as the energy conservations. Today I am going to discuss about how to introduce megawatt scale ESS, energy storage system, to India. I was here in the last conference and tell everybody that our company will lead the stage of the technology demonstration for ESS is over. So we have to commercialize products. This is the containerized lithium-ion battery, 1 megawatt power by 1 battery. So we try to sell these products, commercial products, to the market in India. In the first phase, very negative reaction. One of the major comments is ESS is not proven technology. So we reply that it has been already demonstrated. Many governments in the world has spent enough tax money to prove it works. And also that the MHI, our company, we call ourselves MHI. MHI is willing to provide the idea of build, own, and operate for you. So all technology risks, we are ready to be on our side, not yours. And another comments. We heard more than 100 times in this conference that it is expensive. And our reply to them is, it is expensive if you try to evaluate that as the energy, I mean kilowatt hour price, because energy storage is never be the generator. So you have to evaluate utilizing what is the savings, what is the cost, or another fuel cost saving or reliable power, whatever, you have to make a new value. Otherwise, you cannot tell whether it's expensive or cheap. Then last and also major comment was, okay, many battery people come here, explain is good, but I've never touched battery before, so I don't know how to use it. So our idea or our sales is that, okay, we are the company who can integrate all the systems. We are OEM of the diesel generator, we are dealing with the renewables, so we know everything. So we can, all we need is give me the load pattern and how much you pay for the energy. Then we can integrate all and optimize the system by ourselves, not as a consultant, but we'll come back with you as a real proposal to you. Then after we discussed, the second phase was very positive. Because we are proposing not only the system, but also entire energy management system or service. Like, all those combination of diesel generator, wind turbine, renewables, and energy system, and including everything under one control system, which will speak with the grid and user as a single source. So when we propose that kind of real system with the calculation of the real savings, then people start saying, now I can reduce my diesel fuel cost. It is very good. Electricity bill will also go down. It's very good, so it's very positive. And also that people say, I can have reliable power. This is very good, very important in India. And also the people start saying, okay, I can increase, this is the IPP power producer of the renewables. I can increase my revenue by aggressive guarantee and so on. So this is very good. So we felt that, okay, soon purchase order will be there, but not happening. The voice of client, the phase 3, this is good, but no investment. Now, why? The major comments given by many clients has been, this is good, but grid situation may be improved. That's what the government of the state is saying. It will be improving next year. So, if it is improved, the value of the energy storage system will disappear. We say that, okay, we make it mobile, so if the thing is changed, we can move it to the another location. Or we can provide equipment cells, but it didn't work. Another question, the comments. It is very good to have a reliable power, but it is very difficult to quantify that value. So I cannot sell this idea in the board of directors because I cannot put the price tag on this value. And the last one is, I should wait. I should wait until the ESS, energy storage system cost, is coming down, as it did for power of the renewables and wind turbine. And we are saying that no, you have the very great advantage, but if you wait, you are losing the advantage, but it didn't work. So those are the three major reasons, so that, okay, we will come back later, and it didn't work. Let me go into a little bit detail for the case study. This is the installation for the renewable. Okay, adding the ESS to the wind farm. Obviously, the out guarantee will be easier, as well as the curtailment power can be used for the time shift. And so we propose, and but conclusion is, again, merit understood, but no investment now. It's mainly because, again, the grid may improve in near future. Or current market mechanism does not secure any additional revenue for the grid service. You know, the consultant like CES telling us that potential market huge. So Mitsubishi, why don't you invest your money to this potential huge market in India? It's a gigawatt market. It is only for the renewable. Okay. The answer is, sorry, I couldn't sell this in my management unless we can quantify. The potential market is only potential for the real private capital. The another case study is for the diesel generator replacement. This particular case, the diesel generator is operating every day 4 hours because of the grid situation. So it is not the emergency generator, it's a daily power supply for the buildings. And we propose, obviously, the combination of PV and ESS. Sorry for the small figures, but currently this building owner pays how much? $6 million for the power from the grid and $9 million annually for the diesel fuel. So total $15 million only for the energy. It's a big buildings. So we propose, why don't you add PV and also ESS, and most importantly, the total energy management system, which includes the control of the existing DG to make the optimized operation. And that simple allocation will reduce the fuel bill about $6.3 million per year. So even with so-called very expensive lithium ion, payback time will be very small. Okay? This is a very good example that the new technology can save your energy bill. And we also propose not only selling the equipment, but we can make, again, we build, own, and manage, and we provide a service. If you agree to give us that kind of service fee, again, it didn't work. The main reason is the same. The grid situation, actually, the state government announced that it will be improved within 2 years. So, again, this client come back to us. It is very good, but no way that we can make this happen in the board of directors meeting if the situation will be improved in 2 years. By the way, they didn't believe that it will be in 2 years, but it is announced. And we also tried to explain to the state government or the ISO, kind of ISO, it's a grid operator, that if we adapt this kind of system, we can have a very good backup power source to provide the demand response or frequency regulations or whatever, or backup, emergency backup service to your grid. But unfortunately, that revenue is also not possible because it is not allowed in the current market mechanism. So it stopped. So this is the results, summary of 1 year struggle by Mitsubishi Heavy Industries to sell this commercially proven technology to India. By the way, again, the huge market potential. That's what we have received from the consultant. But still, I do not believe that we can put any capital investment under these circumstances. So how to introduce the energy storage system to India? So supply side, we have to do equipment cost down and make in India, but this is chicken and egg. Market has to be there so that the private money can make an investment in India and goes down. And business model, we propose the services, not selling the equipment. We build, own, and operate the system for you. And user side, that if you have a problem of the technology, participate in demonstration projects and do something to make it move. And we're also discussing with the Japanese government. I think we need the special finance from the government to introduce this kind of new technology to India. And finally, the biggest challenge or request is the government and governments of your country, both central and state. The support the demonstration and definition of new market mechanism and support special finance to be arranged by government of Japan. So everybody has to work together to accomplish the common goal. So our step for the next 3 months is number one, this August, MNRE announced the Renewable and ESS Integration Demonstration Project. So we are discussing with the local partner. Actually, this Monday, I was in the headquarters of Tata Power, and we both agreed, okay, we will jointly bid this demonstration project. It is not for the demonstration of the battery technology, it's a demonstration of system works. And there is a merit for somebody, so that those somebody can start considering how to use those merits. So it's a more system and business model demonstration. That's what we agreed with the Tata Power. And this January, the January of this year, MNRE and METI, which is government of Japan, agreed to conduct a joint study for special finance scheme for introducing energy storage system. So the METI, our government has valued this agreement and did the bid for the feasibility study, and MRI, the representative is here in this conference, Mitsubishi Research Institute, he is the one who got the fund from our government to do this study with MNRE. So MHI and Tata Power will help this study. The third one, as we speak, as we hear, last year the Ministry of Power issued Smart Grid Roadmap, and it clearly mentioned that the new market mechanism, such as demand response, will be introduced in due time. So we really want to discuss to find out if it's coming or it's just a dream with the government. So hopefully I will be able to come back next year, this conference, to tell you those are the successful. If I'm not here, please consider MHR will be back when market is there. Thank you very much.
Thank you, Watanabe-san, for continuous efforts from Mitsubishi to figuring out not just about technology, but also working with business model, and also bringing in the support from Japanese government for facilitating the regulatory side of it through continuous interactions with MNRE and other regulatory agencies. Because again, ultimately, if we have to make this industry work, it's going to take lots of effort, and if everyone just waits for someone else to do the work, again, 10 years down the line, we'll be talking about same things. Because again, I think as a country, all of us are very optimistic, and everyone feels that in 2 years the grid situation is going to change. But probably for last 50 years, we have seen that it hasn't changed. So again, thank you very much for efforts from you personally as well as Mr. Vijay. I'd like to invite Dr. Deepak to talk about some of the advances which have been done by Exide Industries on lead acid. Because again, we are hearing about lots of new technologies, but lead acid has been the backbone of energy storage industry for over a century. And again, companies like Exide have been working on new innovative solutions so that it can remain a key player in for next century.
Thank you, Rahul, for very encouraging words. Very good evening. A quick introduction. I'm Deepak Chaudhary. I'm from Excite Industries Limited. Excite as a company has been in this country for more than 60 years. We almost exclusively deal with lead-acid batteries, but not necessarily limited to it. We are also doing some work on lithium-ion. For example, the small electric car which is parked in the exhibition hall, which is the one which has been done by the Microgrids, is powered by the lithium-ion battery given by us. Okay. I think, having said this, I realize one thing, that more so particularly because there's a presentation from Tesla right after me, people would be a little bit impatient to hear about lead-acid batteries. Lead-acid batteries are boring. And I'm almost envious of the lavish praises which are heaped upon on all the alternate chemistries which have emerged over the last decade or two. However, having worked in this industry for 30 years, I almost owe it to my future generation, to the next generation of engineers who are in my organization as well as anywhere else, the other organizations in the lead-acid battery industry, to take them through to the coming decades also. Because that way, I am very, very confident that instead of getting into a competition with the different chemistries which are around, they can be complementary. Because nothing can be, unfortunately, a euphoric solution. 30 years back, when VRLA was introduced in the world, it was considered as the ultimate utopian solution. Fit it and forget it. And I think more than India, Europe and USA learned it very, very seriously over 20 years, that the so-called seal maintenance free was neither seal nor maintenance free, had no possibility of delivering the initially promised 20 years of life, and could deliver life as low as even 2 or 3 years, when the manufacturers used to tell about 20 years. So instead of getting into it, I think I need to look into my technology, the lead-acid technology, and I'll take you through a very brief presentation. I promise you it's going to be very brief. It's quite late in the day. Even I have time to catch late in the evening, so I won't take much of your time. Now, when we talk of advanced lead-acid batteries, let us understand that what is advancement that we talk. When we talk of advanced, we basically mean either of these. There are paste additives which really give it a much higher charge acceptance. My job has been made a little simpler because this morning, if I remember, there was a presentation by Panasonic who very clearly outlined the basic, what you may say, the reasons of people being fascinated by lithium-ion and the subsequent technologies are very fast charge acceptance, ability to survive partial state of charge, and third was ability to deliver a very large number of cycles. Now, if I keep these three in my focus, I think they are all three totally interrelated, and it starts from a battery being able to accept charge much faster. And when we talk of charge faster, when we talk of charging at rates of 1C or maybe 2C, that means a 100 ampere hour cell getting charged at 100 amps or 200 amps or maybe even at 300 amps. That is what we are basically looking at. So, bulk of the work that has been done in advancement of lead-acid batteries has been towards this, that how can lead-acid batteries be charged faster and faster? And what are the additives which can facilitate the acceptance of charge at this very high rate? There have been other features also, additives in the electrolyte. There have been changes in the grid geometry, the manufacturing technology, all taking it towards a much higher energy density, because energy density is also a factor. Not that we can do much about lead. Lead's atomic weight will remain 207, I think, in the near future. You won't be able to change that much, so lead will be heavy. So that's one thing we have to accept. but we can work on the rest. We can give a much higher energy density, and we can try to match the charge acceptance, the partial state of charge of the battery. So, coming to additives, it is also mostly in the negative active material, because please understand that lead acid is an aqueous system. So invariably, when the battery reaches around 80-85% state of charge and you try to charge it beyond that, dissipative reaction of water starts, and this interferes in further efficient charge acceptance. So also, the fact happens that during this time of repeated charge and discharge, it is the negative active material which tends to sulfate and slowly lose surface area and accept less and less charge. So whereas a lot of tests have also been done on positive active material additives, for the sake of this particular discussion, I will limit whatever we have done for the negative active material. Having said that, we have no intention of making this a battery technology conference. I know this is an application conference. So I'll very quickly switch over to the application part, saying that in the last decade or so, there have been very substantial improvements in the charge acceptance of lead acid batteries. And today, a negative plate which is dosed with appropriate quantities of additives, which are carbon-based, not necessarily carbon, but some other material also, can be charged at rates as fast as 1C or even 1.5C, which is quite competitive. There have been other additives which have also addressed the positive. So overall, we are in a situation that on a practical scale, I mean, it's one thing to be nice to be very hypothetical that I can charge a battery in 10 minutes or 15 minutes, but in a practical sense, we can deliver a product which can be charged very fast. I now come to the Indian telecom application, which very kindly Mr. Manohar has mostly elaborated. I'll go through it very quickly. I'll just tell you that the woeful power condition of India is known, that more than 50% of the telecom towers in the country have at least 8 hours of power cut. And perhaps around 40% have a minimum of 12 hours of power outage in a day. As you can well understand, under a conventional condition, and particularly a VRLA, which purely from the maintenance and the space consideration point of view has been the only choice of telecom operators, perform very pathetically under this condition. Each of these towers, I'll go through it very quickly, which has a 48-volt battery bank. It has a 10 to 15 kVA DG set, and DGs are on an average run every day for 6 to 12 hours. These are some figures which I have picked up from the telecom operators' websites only, or their presentations which I have attended, that annually the DG sets consume some 2 to 2.5 billion liters of diesel, which is equivalent of rupees 120 billion in value, and emits 6.5 metric ton. AGM VRL batteries, which are currently in use, deliver 3 years in life, but that's a very brave statement. Actually, they deliver somewhere around 2 years, but all of us manufacturers keep changing cells, we cannibalize it with new cells and etc., and somehow establish a record that the batteries are performing for 3 years. Frankly, it does less than 2 years. And energy cost for the tower operators itself is 35 to 40% of the total operating cost. Under this condition, I don't need to emphasize, I think this has been the theme of this conference, that the immediate priority is to reduce diesel consumption altogether. And also there are these advisories which have come from TRAI that 50% and 33% of the towers in rural and urban will have to have hybrid power. So the hunt is basically therefore for technologies which would deliver on a daily basis 18 to 20 hours of power and recharge in 4 to 6 hours. So what are we basically looking for? Let's define what is expected of the battery. One thing, if it is to operate in India, it has to be highly resilient to high temperature operation. And typically, let's take a benchmark target of 8 hours of discharge and 2 hours of charge cycle the battery should be able to perform. It should be able to survive partial state of charge tolerance, and in order to deliver a 5 years life, it should be giving a minimum of 3,000 cycles. So, what would be the ideal strategy? And this is where the new paradigm for lead acid batteries. Do not try to charge it to 100%. Charge it only about somewhere between 30% to 70% or 40% to 80% or so. Do not try, because the more you're trying to charge it beyond 85-90%, you're wasting energy and your charge is much, much slower. Excuse me. Number 2, having not recharged to 100%, you must be able to put in features into the battery so that it can remain at continuous cycling in partial state of charge without losing any capacity of it permanently, and achieve a cycle of 3000. So towards this end, what Excite has been doing, moving into 2 directions. Excite has been introducing the advanced tubular gel batteries in the telecom market, and an investigation has also been planned with what I'm sure many of you are familiar with, the ultra technology. Now, why gel? Our fascination with the tubular gel starts from the fact that these are certain figures which we picked up from the literature, that it cycles very, very well, even at very high temperature. It also requires the minimum recharge. More important, this was the clinching factor why we chose tubular gel as a vehicle, because this is one technology which, on a cycling mode, is relatively immune to temperature. It just does not lose cycle life very fast as the temperature goes up. So doing this is the case study of the application that we would like to describe to you, that there are today towers very close to Delhi where we have put up these tubular gels which have been working for the last 15 months, and there have been certain guidelines, certain issues that we have been able to discuss and convince the telecom operator. And I'm very happy that after 15 months these are working very well. They are now talking of taking bulk lot, and the other telecom operators are also started inquiring. I think we have just got some further education order for the telecom operators. What has been the trick? Why has this been a success? A is the intrinsic character of a tubular gel. B is the fast charge characteristics of the advanced tubular gel. C, you will also notice over here, to take advantage of a fast charging, instead of 24 cells, we have given only 23 cells. This has been able to raise the charging voltage and deliver the rechargeability even better. Under this kind of condition, in situations where there are a cumulative of 18 hours of power cut in a day and 6 hours of only recharge through either mains or through DG, the batteries are performing perfectly well for more than 15 months. We will be waiting for another 8 to 9 months before we would start publishing this data in a much wider scale, but this has been the success. I think this has given a lot of encouragement to us in the lead acid that we can figure out solutions for the Indian telecom. I will just go to the last part of my presentation, which will be more visual, I'll talk less, is we now move over beyond the tubular gel to the realm of the ultra battery. I think my friend John Wood yesterday had already introduced you to ultra battery. Ultra battery is a totally new dimension in the world of lead acid battery, where we have been able to actually incorporate an asymmetric capacitor as a part of the negative plate. This entitles it to very, very unique characters which include recharging at rates much higher than 1 hour. Today, with our advanced tubular gel, we are talking of a paradigm where we are going to discharge a battery for 6 or 8 hours and recharge in 2 hours. In ultra battery, it should be possible to recharge it in 1 hour. Again, when we talk of recharge, we don't intend to recharge it to 100%. We will recharge it, say, within a level of maybe 40 to 70 or 80%. Now, this is the technology that we have now felt that would be the most appropriate, because the application is shifting from starter battery to motive power battery to standby battery. The typical load cycle of a partial state of charge, frequent discharge and charge, maybe even at milliseconds level, seconds level, is something which is getting addressed by ultra. Excite today is partnered by Eastpec in the USA, eColt, and we propose to bring in this technology and put it on trial into our specific telecom application. This is a technology which has already proven its worth for some of the most challenging applications which have been discussed for the last 2 days on load leveling or peak shifting or microgrids in particular. It has established its credentials, and even in frequency response for last 3 years it has been in operation with absolute comfort in USA in the PJM installation. Ultra battery has this unique character that it completely smooths out the intermittency of the availability of the renewable power. So it is perhaps going to be the most appropriate and the most, what you may say, the best fit solution for renewables. Ultra battery as a concept will be most fit for the frequency regulation, where the frequencies, the demands of the battery can be as severe as that. With that, ladies and gentlemen, I come to an end with just the message that the lead-acid battery has covered a lot of distance. Do not compare when you talk of lead-acid only to that of a VRLA. The lead-acid is much beyond it. And it has features, and as a total package, as a technical package, it can challenge any of the competition. Thank you.
Thank you, Dr. Senthilji. And again, I think there are lots of people in the room who still appreciate lead-acid and are looking forward to continued usage. So what we as India Energy Storage Alliance believe is that there are enough applications where we need to have continuous innovation and look at ways for matching different technologies. And I think there is, again, as we have been saying, there is enough market, but we just need to come all together and make sure that that market really materializes. But without any further ado, I know a number of you have been waiting for the next presentation. So I hope, Arjun, no pressure on you, but yes, I think you have taken it on yourself. So again, Arjun Padmanabhan from Tesla is going to talk about, not about the electric car, but actually how Tesla is looking at using some of the innovations that are used for bringing energy storage in electric cars to also stationary applications.
Good afternoon, everyone. My name is Arjun Padmanabhan, and I am with the energy storage team, the stationary energy storage team at Tesla Motors. Thanks to Rahul, one of the conference organizers, for inviting me here to share Tesla's perspective. And as a community that I follow, Dr. Chaudhary, I do believe that lead-acid batteries have been the mainstay of storage solution ecosystem for a couple of decades now. And as we develop new lithium-ion technologies, I think it's sort of an evolution of technology that serves or provides an appropriate solution for new applications as they emerge. A little bit about stationary energy storage at Tesla. We started working on energy storage about 4.5 to 5 years ago as a small R&D effort within the organization. It was a relatively clandestine operation in the company. As a public-facing company, we've been maintaining our primary product as being our focus area, which is electric vehicles. But needless to say, this has been an effort that's been ongoing. What you see here actually is an image of 1 megawatt, 2 megawatt hour battery installation. That's, the pointer here works. That's a 1 megawatt, 2 megawatt installation that's right outside our electric vehicle manufacturing facility in Fremont, California. It's a modular technology that comes in 400 kilowatt hour blocks, and we'll talk a little bit more about that in a second. But we've had systems installed and operational for over 2 years now, providing reliable functions and applications for C&I customers. At a higher level, what is Tesla's motivation for working on energy storage? It's actually multifold. At the beginning of Tesla, we started working on electric cars because we wanted to solve or minimize global dependence on fossil fuels. And that meant trying to solve the largest problem that existed in terms of transportation, which is the largest consumer of fossil fuels. And as we think about an increased amount of penetration of electric vehicles and increased penetration of distributed generation, we see the grid facing challenges that it's never faced before, and a natural solution for that, for the evolving grid of the future, is energy storage. A little bit about Tesla as a company. We were founded in 2003, about 10 years ago. We've since grown to be a company that's about over 10,000 employees. We have a large manufacturing facility. It's about 500 square feet, again in California, which is serves as the sole manufacturing facility for our cars today. It served as the manufacturing facility for the Roadster, which is our initial electric car, about 2,500 which we produced. It currently serves as the manufacturing facility for our Model S. of which will produce about 35 to 40,000 cars. And then our next generation vehicle, which is the Model X, is going to be manufactured out of this facility as well. This facility also serves as a primary manufacturing facility for our stationary storage products. And those are the vehicles I talked about. Outside of the vehicles that we've manufactured ourselves, we've worked in close partnership with companies like Toyota and Daimler Mercedes to support the development of their electric vehicles, which essentially use the powertrain that sits in our car. So when I talk about the powertrain, I'm talking about the battery management system, the thermal management system, and the power electronics that couple together to form the powertrain. And in terms of deployment expertise, we have over 40,000 vehicles globally deployed now across 40 countries. We have about 500 million miles of data. So when we talk about storage experience, we have about 2 years of stationary storage deployment expertise, but we have nearly over half a decade of data coming from batteries on the field, not just for stationary applications, but in fact on a mobile platform, often driven over 70 miles an hour. And that cumulative pool of energy storage systems that are out there represent about 4 gigawatt hours of batteries or cells that have been deployed, and combined with over 12 gigawatts of bidirectional inverters that go in the vehicle for driving the vehicle. Currently, our manufacturing capability is in the order of about 3 gigawatt hours of lithium-ion cells that are consumed in native battery packs for both the electric vehicle and the stationary storage product line. The stationary storage product line, nonetheless, is a much smaller portion of our business today. We're producing about 100 megawatt hours of batteries, and that are being installed. In fact, I'll talk about that in a second here. We have close to about 40 megawatt hours, or roughly 20 megawatts of batteries installed today, and by the end of the year, we should have close to about 80 megawatt hours installed. By 2017, we expect to have a substantial amount of growth in the number of electric vehicles that we're manufacturing, as well as a substantial growth in the deployment of our stationary storage systems, both in the United States and outside, especially in India. And in order to meet that growing demand for cells and for batteries and for finished products, because you may already be aware of this, we are currently manufacturing what we believe is the largest battery manufacturing facility in the world today. It's called the Gigafactory. It's going to be located in Nevada. It will have a cumulative production capacity of about 50 gigawatt hours when it's fully operational in about 2020. We'll have the ability to support the manufacturing of about 500,000 cars per year. Roughly 35 gigawatt hours of that of battery capacity coming out of the factory will be cells that will be manufactured in-house. And roughly 15 gigawatt hours of that will be cells procured from external vendors but assembled into battery packs in-house. Probably important to mention here is that this scale of operation is unprecedented, which means it allows us to get to economies of scale, both for electric vehicles and stationary storage, that we believe will be market-making in a lot of ways, and transformation to the market. And going back to one of the earlier slides that Rahul had yesterday at the opening of the conference, we do see a price decline tied to the scale of manufacturing that we believe will disrupt the market significantly. In terms of the technology itself, Tesla is particularly obsessed with vertical integration. We talked about challenges with battery systems containing components that are disparate from different battery vendors and different inverter manufacturers, power conversion system developers, and so on. We're taking a page out of the same book from our electric vehicle R&D days, where we managed to package together, if you look at the image here, the battery pack coupled with the drive electronics coupled with an AC induction motor, which essentially serves as an AC load that's driven by a bidirectional inverter, and it can charge and discharge as needed at high C rates when needed or low C rates depending on what mode of operation you're in. So taking the same technology pieces that go in there, we took the BMS components and the thermal management components and repackaged that to develop our commercial and utility scale building block or modular system we like to call a superpack. That's roughly a 400 kilowatt hour AC rated battery pack coupled with either 100 kilowatts or 200 kilowatt power conversion unit, giving you a 2-hour or a 4-hour system, which needless to say has a lot of flexibility in how you operate it. And it also is self-contained in that it has a thermal management system that does not require the need for an external air conditioning system or a thermal management system outside of the outdoors of the pack. In terms of the product overview itself, we've from the automotive battery pack, which is roughly 55 kilowatt hour DC pack. We began with a relatively small residential pack that was a roughly 10 kilowatt hour system, which we deployed quite a few of in partnership with companies like SolarCity. Point worthwhile to emphasize here is SolarCity is one of our early partners, but by no means our only channel partner for deploying these storage systems. We've worked with several solar developers and energy efficiency providers to deploy our storage systems, and we look forward to continuing to do that in other markets as well. And for the utility scale or commercial scale systems, across about 50 sites, ranging from commercial industrial installations to certain utility-tied, grid-tied systems to microgrid applications on islands, we have currently about 40 megawatt hours of systems deployed, and like I mentioned, by the end of this year, we expect to have close to about 100 megawatt hours deployed. By design, the system is extremely scalable and modular in the sense that each of these building blocks you see here is a 400 kilowatt hour battery pack that's AC coupled to the building. So in the unlikely event of one of the systems being out, the rest of the system continues to operate just fine. Going back to the analogy that Mr. Manohar from Reliance talked about, this also enables you to go to larger scale systems with sort of a centralized battery management system that has built-in intelligence to operate in different operating modes. In terms of applications, we've installed applications, we've installed systems that serve applications such as load shifting and peak shaving, which perhaps are value streams that are most beneficial to commercial and industrial customers. But we've also demonstrated applications ranging from demand response to ancillary services with our systems currently in California. We're also currently discussing or in discussions for projects ranging in the hundreds of megawatt hour scale systems being deployed directly with utilities. I talked about some of the projects we've currently completed. This is a project at a winery in California where we have a 1200 kilowatt hour system with 2 hours of integration. This is a utility scale project where we can get multi-megawatt scale systems by installing multiple of those modules. These are residential and small commercial systems that can be used either in combination with PV or as independently used storage systems, such as for telecom towers. We have 200 odd units currently interconnected, total about 400 units that will be operational by the end of the year. And we're already working on our next generation system based on what we've learned from our installations over the last couple of years. Looking forward, we see a lot of interesting applications in India, particularly on the grid scale. We also see a lot of near-term applications in the microgrid scale. I think in the long run, as we see increased penetration in distributed generation and increased penetration of EVs, a residential scale storage system in every single home is not too far away in the future. That's all I have. Here's a gratuitous picture of our car. Always happy to stick around for more questions. Thank you so much.
Thank you very much, Arshin. In the interest of time, I think we will be transitioning straight to the next panel, which is almost a continuation where you left the car. We will be transitioning into the e-mobility panel, but hopefully the speakers will be here at the end of the next panel so that if there are any questions, we can all talk together. I'd like to thank all the speakers for excellent presentations. Apologies for not able to take any questions at this moment, but because I know that there is an excellent panel for electric mobility, and some people have hard stops in terms of catching flights, so we'd like to hand over a token of appreciation.
A big round of applause for all the speakers for the last session. Mr. Takaya Watanabe, Dr. Deepak Senchontri, and Mr. Archan Padmanabhan. A big thank you to all the speakers. With that, we come to the last discussion for the day, and that's a panel discussion on electric mobility. In interest of time, I'll directly introduce the speakers for the next session. It would be great if all of them can join us on stage. The moderator for the session would be Mr. Dipanshu Dev Sarma, Editor-in-Chief, Autotech Review. Before joining Autotech Review, Dipanshu was the editor of Automonitor and was working for Network 18 Publishing. Currently, he is responsible for the overall business of the entire magazine. Next, we have Sri Sujit Mishra, Senior Divisional Electrical Engineer, Lucknow Division, Northeastern Railway, Ministry of Railways. He has been instrumental in the design of new classes of electric locomotives and laid framework for the introduction of new generation of control and communication and drives for the electric locomotives for the Indian Railways. Our next speaker is Mr. Sajid Mubassir, Member R&D at National Automotive Board. Previously, he was working with Ministry of Science and Technology. He has been a vocal, committed and pushy participant in the stakeholder forum for the National Mission on Electric Mobility. Currently engaged in developing a technology platform for electric mobility. And last but not the least, we have with us Mr. John Wood, the Chief Executive Officer of eCult. He joined the energy storage community in 2008, having previously launched technologies globally in security, identity, payment technology and telecommunication. Can I please have all the speakers on the dais, please? So everyone's pretty thirsty by the end of the last discussion. So what we have for you is anybody who's outside for tea break can get over your tea inside and enjoy the panel discussion as well. So it would be great if we can have everybody back in the room along with their tea, coffee, and be a part of the panel discussion on electric mobility.